Ah, okay, very large scale integrated circuits or very large scale integration. Okay, we have seen evaluation. Next, what is IC? IC is a integrated circuit, and definition is a it is a very miniaturized low cost electronic circuit, okay, consisting of active and passive components and a single silicon chip. Okay, how this substrate or vapor is fabricated? Okay, this is the process. Okay, why we use integrated circuits? Because of, okay, these are the advantages. Okay, because small size, low power, very compact, and high density of circuits. Okay, these are the okay, based on the, okay, classification. Okay, based on three types. Okay, based on the application and level of integration. Okay, and based on the fabrication, there are three types of integrated circuits. And the basis of fabrication, Sharat. Okay, but here not showing. Okay, I will. Okay, admit. Okay, here I am sharing the screen. It is not showing. Okay. Anybody is joining, you can indicate me. Okay, I will admit him. Okay, here mainly these ICs are classified based on the fabrication, application, and integration. Okay, based on the fabrication, okay, there are following steps: monolithic ICs and monolithic, thick film and thin film hybrid ICs. Okay, these are based on the fabrication and okay, based on the application. Okay, linear ICs and digital ICs. And level of integration, SSI, MSI, LSI, VLSI. These are the, okay, classification of ICs. Okay, last class up to we have is the, okay, thin film and thick film integrated circuits. Okay, here what is thick film and thin film integrated circuits? Okay, this is also IC. Okay, these ICs are larger than monolithic ICs. These ICs are larger than monolithic ICs and smaller than discrete circuits. Okay, these electronic circuits. Okay, these are all bigger compared to. Voice is not clear. Okay. Uh, I think signal is low signal. Now it is clear. Uh, okay, these thick and thin film ICs are used in high power applications, and these are cannot be integrated with diodes and transistors. Okay, diodes and transistors, if required, can be externally connected onto its corresponding pins. Resistors and capacitors can be integrated. Here, these resistors and capacitors can be integrated using the this thick and thin film material, semiconductor materials. We can integrate, but these diodes and transistors, okay, here cannot be integrated. Okay, now we will see the difference between thick film and thin film integrated circuits. Okay, here thin film. Not clear. Just your voice is not audible or not clear. Okay, okay. Here, thin film integrated circuits. Okay, here thin film integrated circuits. See here, fabricated by depositing thin films of conducting or semiconductor materials on the surface of a glass or ceramic material or ceramic base. Okay, here just depositing the semiconductor material on the glass. Okay, this thin film IC is fabricated or we can make by depositing the some semiconductor material. Okay, here resistance of the this IC can be calculated using the this formula R equal to rho L by A. Okay, here rho is the resistivity, L is the length, A is the area of cross section. Okay, based on the resistivity of the semiconductor material, we can calculate the resistance of the particular area. So you can here you can obtain the resistance by using this thin film IC. Using this formula, we can get the resistor, and likewise we can get the capacitor also. Means depositing the two semiconductor materials in between insulator, you can get the two uh, plates in between dielectric material. So here also we can get the capacitor by using the thin film IC, and by controlling the thickness and width of the film we can fabricate resistors of different values. Means the thickness of the layer material layer, by controlling it we can fabricate the different values. Different material will have different resistivity. Similarly, capacitors can be fabricated by depositing two conducting films separated by an insulating layer, that is dielectric. An inductor can be fabricated by depositing spiral form of film onto the IC. Okay, here resistors, capacitors, inductors can be fabricated on the thin film IC. Okay, if you see here thick film IC, commonly used as a printed film circuits. Okay, it is called as a commonly called as printed film circuits. A screen printing or silk screen printing technique is used to obtain desired circuit pattern on a ceramic substrate. Means if you see uh, if you see the printing layer printing on any if you see any cards, okay, uh, some thickness we can see, that is screen printing. Okay, thick film integrated circuit is also called screen printing. Okay, this when we apply some inks on the paper, okay, we can see the small thickness of printing. If you see in the wedding cards or some other cards, we can see the screen printing, this technique. Okay, that is come under the thick film IC. The inks are used for printing the circuits. Means different materials. Ink consists of materials that have resistive, dielectric or conductive properties. The screens are actually made up of fine stainless steel wire mesh. Films are fused to the substrate after printing by placing them in hot high temperature furnaces. Okay, by using these, okay, substrate or wafer, we can put it in the high furnace and depositing these inks, whatever the material we want to deposit, okay, we can place. And this that paper or any glass will be coated by the that semiconductor material, or okay, whatever the material we want to deposit, we can deposit. Okay, that is thick film integrated circuit. Now, what are the advantages with compared to monolithic ICs? Okay, if you see advantages compared to monolithic ICs. Okay, better tolerance, better isolation between components, and flexibility in circuit design. Okay, here monolithic ICs, here we can add monolithic means single stone. Okay, single stone we can fabricate the IC, but here isolation between the beside transistors or circuits is not possible. It is difficult for the isolation. So, but in the thick and thin film ICs, here isolation is good, and flexibility in circuit design, okay, better tolerance. Thick and thin film IC technology can't be used to fabricate active components, as it will further result in increased size. Okay, because of size problem, thick and thin film IC cannot be used for the active components, means uh, diodes, transistors, and these active components we cannot fabricate, because when we fabricate these active components, size will increase. Okay, that's why we cannot use thick and thin film ICs. Okay, next, here if you see hybrid or multi-chip integrated circuits. Hybrid or multi-chip integrated circuits. Okay, here what is here hybrid or multi-chip integrated circuits? Okay, the circuit is fabricated by interconnecting a number of individual chips. Means here number of individual chips can be interconnected. Means on the PCB, okay, we can integrate or we can interconnect number of ICs. Means for example, one 555 timer IC, one is microprocessor IC, one is different microcontroller IC. We can interconnect using the connecting wires. Okay, that is called hybrid or multi-chip integrated circuits. Means many ICs we can interconnect. Okay, you can call it as hybrid ICs or multi-chip integrated circuits. Okay, these hybrid ICs used for the high power audio amplifier applications. Means we can integrate number of ICs. So we can use for high power audio amplifier applications. Diffuse transistor or diodes are the active components, and diffused resistors or capacitors on a single chip or thin film components can be some of the passive components that can be fabricated. Means here multi-chip, so we can integrate more number of active and passive components can be fabricated. Means diffusing of resistors or capacitors we can incorporate in that the multi or hybrid ICs. Metallized pattern or wiring is used for interconnection between the individual chips. Okay, here we can use metal pattern, means deposited metal pattern we can use, or wiring is used for the interconnection of the different ICs. Okay, next Moore's law. Okay, here what is Moore's law? If you see here, if you see here, Moore's law. In 1965, Gordon Moore, an industry pioneer, predicted that the number of transistors on a chip doubles every 18 to 24 months. Okay, an industry pioneer, an industrialist. Okay, in the 1965, he predicted that number of transistors for a chip, okay, doubles every 18 to 24 months. Means every 18 to 24 months, the number of transistors in a chip doubles or increases. He predicted. He also predicted that semiconductor technology will double its effectiveness every 18 months and many other factors grow exponentially. Moore also stated that silicon technologies will double the number of transistors per chip every 18 months. Okay, because of the advantage of silicon compared to other semiconductor materials, this silicon technology will double the number of transistor per chip every 18 to 24 months. Okay, the fabrication of ICs, more than 95% of the ICs fabricated with the silicon technology. Okay, in the present IC fabrication, the 95% of the wafers or substrate are fabricated based on the silicon technology. Okay, that's why he predicted that every 18 to 24 months, this number of transistor per chip increases. Next, here design challenges. Okay, if you see the design challenges, uh, in producing smaller systems and reducing power dissipation, IC manufacturers are facing major design. Okay, yeah, okay, IC manufacturers are facing. Okay, time is going to end. Okay, if possible, I will extend up if meeting ends. We can extend other 15 minutes. Okay, I will put the link. You can join in that meeting. Next, okay, if automatically it closes, then I will put the link. You can join immediately. Okay, now what are the design challenges? Okay, in the IC manufacturers. Okay, there are mainly three categories. These IC manufacturers are facing the design challenges due to the following constraints. Okay, what is first one is power density. Next, I dynamic power dissipation, I static power dissipation. Okay, uh, because of number of circuits, okay, circuit complexity, here power density also increases, and I dynamic power dissipation means okay, during the when the IC is on means IC is operating. Okay, here okay, how much power is dissipated, and during the standby mode, okay, static mode, how much the power is consumed. Okay, these are all the design challenges for of IC manufacturers. Okay, these design challenges can be overcome by improvement in design, material, and manufacturing process. Okay, these can be overcome by the Yes, it is coming. Okay, okay. These design challenges can be overcome by the major two steps for major aspects of successful design. Okay, first one is approach to system design cycle and workable transistor models. Okay, first one is system design cycle. Okay, next one is transistor models. Okay, here system design cycles. Here system design cycle. The design process of IC technology starts from algorithm, then follows architecture level, logical level, and finally approach to layout level. Okay, these are all the system design cycle: algorithm, architecture, logical, and layout level. The input to the algorithm level are from arithmetic operations and number system. Okay, you can see the flow chart. Here flow chart if you see, okay, here input to the algorithm level is algorithmic operation or number system. Next architecture level, okay, logical or floor plan level or layout or logic gates level. Okay, these four steps are the main for the system design cycle. Here physical layout can be realized for low power dissipation and minimum area per chip after going through different levels of system design. Next one is transistor models. Okay, first system design level and transistor models. Here transistors are electrically controlled switches with a control terminal. Bipolar transistors requires small current into control terminal for switching. Okay, whereas MOSFETs offer advantages over bipolar transistors as they draw almost zero control current. Here, BJT is the current control device, MOSFET is a voltage control device. Okay, here BJT requires small amount of current, okay, for the switching, but whereas MOSFETs, okay, zero control current required. Okay, because of this advantage compared to BJT, okay, we can use MOSFET models. Okay, transistors models are characterized by, okay, various factors. Okay, some of these okay models their okay characterized factors are: first one is performance, okay, level of integration and cost of production. Here transistor models means the which type of transistor must be used for the fabrication of IC. Okay, which model? General we know BFW11, BFW11. These are the standard type of FET. Okay, like that, which transistor model is good for the IC fabrication, for the application, based on the application. Okay, these transistor models are decided, and these are the factors. Okay, performance, level of integration, cost of production, number of gates, gate delay, die size means chip size, testing, reliability, power dissipation. Okay, these are transistor models, characterized factors. Next, technology integration. Here, if you see here, technology integration. Due to evolution in technology, the electronic products are becoming compact with minimized power dissipation. Therefore, integration of multiple technologies is the driving force for realization of new systems. Okay, now technology increasing and many electronic products are very compact, okay, minimal size and low power dissipation. And because of that technology increasing, these multiple technologies are driving force for the realization of new systems. Okay, if you see here below figure, integration of silicon VLSI chip and opto VLSI processor. Mm, okay, here uh, one to many optical interconnect. Okay, here first one is opto VLSI processor. Here silicon chip array. Okay, here integration of silicon VLSI chip and opto VLSI processor. Okay, here the idea of integrating silicon technology with emerging technologies offer new opportunities and challenges. Okay, here intelligence and computational power is provided by silicon chip array, whereas light wave technology or photonics provide optical interconnects by opto VLSI processor. Means here intelligence or computational power is provided by the silicon chip array, and whereas the interconnection will be provided by the opto VLSI processor using the photonics. Okay, optical interconnects. Next, okay, this is before that one is technology integration. Next one is VLSI design styles. Okay, VLSI design style. The circuit performance level within a design time is much dependent on absence of design methodologies and design style. Okay, here performance is dependent on absence of design methodology